Can you hear me now? Oh God, that is not good. Alright, time for me to do my intro one more time. Hello everybody, welcome to Alex Does Leak Code. It's that time of week again where we do programming problems live on stream. So, my mic was off. Thank you, Chien, for pointing this out. Oh my God, what would I do without you? I couldn't hear anything before. Oh yeah, my mic was off. Specifically, I was using the wrong mic for the mixer. Ugh. Either way, so in this case, let me take this chance to announce. I gotta edit this from the stream. Let me take this chance to announce the Leak Code bi-weekly contest. So I don't want to say I, because we are gonna do it together, all of us, everybody on this stream, including you, dear viewer, my one viewer right now. It will be this Saturday morning at 9 a.m. So it is a classic programming contest, which means you will probably get a bunch of questions. I expect you get a bunch of questions, and everybody tries to solve those questions together. And the questions look a lot like the questions that we've been working on this channel for a while. So we're gonna all work on this together. You can do this on your own. I highly recommend doing this on your own. If not, whoever's interested, please drop by my stream this Saturday at 9:30 a.m. Eastern time, whatever that translates to on your time. And we'll work on this together live. There's a 5,000 coin prize, and I think these are just like, I don't know, these are just like fake internet points. So I don't know if that's very helpful. Alright, with that out of the way, let's work on today's problem. So today's problem, it's number 26, remove duplicates from sorted list. Give me a second. I'm gonna increase the resolution on my other screen. Now they have two screens, it's a little bit easier to see what's going on. It's a little bit easier to get feedback on my own channel too, because now I see what you guys see. I can see clearly there's some lag, which I'm trying to get rid of. Okay, so today's problem is remove duplicates from sorted lists. Given an integer array nums sorted in non-decreasing order, remove the duplicates in place such that unique elements appear only once. The relative order of the elements should be kept the same. Then return the number of unique elements in nums. Consider the number of unique elements of nums to be k. To get accepted, you need to do the following things. 1. Change the array nums such that the first k elements of nums containing, this is a lot of words, this containing the unique elements in the order they were present in nums initially. The remaining elements of nums are not important, as well as the size of nums. Okay, return k. Okay, this is actually a lot of words to explain a concept which we will see very often in computer science, where we have an array. We're gonna sort the array, but after we sort, we're gonna ditch. We're just gonna ignore the sort of later part of the array. Okay? So that's what it means by in place. That's what this means by in place. The reason why we do this is generally because this is a bit faster and we don't want to move memory around. And this is true especially for very large arrays. Allocating and deallocating these large arrays, not a good thing. Okay? So the judge would test your solution with the following code. Nums blah nums. Okay, check that. 1, it will check that it's the correct length. 2, it will check that the first k elements are correct. And I want to go through all these examples just to make sure we're on the same page, because this idea of packing the array is a little bit subtle. So for instance, here you see 00111 2, 2, 3, 3, 4. What we want to do at the end is to create an array that has 0, 1, 2, 3, 4 in the first 5 slots. The other 5 slots doesn't matter. The other 5 slots, we don't care. Why don't they say increasing instead of non-decreasing? That's a great question. This is a non-decreasing array. It is not an increasing array because 0 to 0 does not increase. It stays the same. So this is not decreasing. It is this is non-decreasing. It is not an increasing array because it doesn't go up every single time. Okay. Excuse me. Let me take a sip of water first. Okay, so I'm going to paint a picture here, and forgive me if you already understand this concept, but I want to make sure everybody gets this right. Okay? The idea is you have an array, you have a bunch of stuff in the array, and let's say 0, 0, 1, 1, 1, 2, 2, 3, 3, etc. Right? Because we are going to use only the first few elements of the array, right? We're going to use the first 4 items in the array. What we're going to do is we're going to take these items and we're going to move them. We're going to sort of pack the array. We're going to pack the first part of the array. We don't care about the rest of the array. Alright? We don't care about the rest. What happens in the rest doesn't matter. We don't care. That's what it means when it says this. These underscores. So the reason why we want to do this, once again, is because we want to make sure we don't allocate another chunk of memory. This is not that obvious in a language like Python, but when you use C++ and you use even something like Java, for instance, if your array is extremely large, you will notice a certain slowdown. In Python, honestly, I don't think it matters. In C and C++, this was a very, very common technique in the past, where people were sensitive about reallocating large arrays. They just packed the array and kept the rest of the space empty. And then we'll say, oh, this array, well, it's got 200, it's got length 200, but only look at the first 5 things or first 10 things. So that's how people used to do it. Okay, so the way we're gonna write our code is also gonna be very similar. Okay, we essentially gonna do what this picture we've drawn here, which is we're gonna go down the array. We're gonna have a let me pick a different color. White. We're going to go down the array. We're going to have 2 pointers. We'll have a pointer here, and we'll have a pointer that sort of travels down the array. And then every time it sees a new number, it just puts that new number into the current location, and then it moves this pointer by 1. And then it just keeps traveling down again. It finds the next unique number and it sticks it in here. Sorry. It sticks it in here and then it moves this arrow by 1. So that would be our strategy. Do empty spaces take up space? Do empty spaces take up space in memory? Yes, it does. Yes, it does. So this is especially true when you're working with something like C++. If you allocate an array in C++, you explicitly allocate the size, and Java, you explicitly say how big you want the array to be. If your array is of size 1000, it means it's big enough to hold 1000 integers. If you only use the first 5, the other 995, boom, they're useless. So it's not very space efficient, but it is time efficient. And this is really useful when you know that your array is going to grow and shrink later on. You're going to add new things to the end of the array. And then you're going to sort them again and remove duplicates again at the end of the array. Yeah? So this is really helpful in certain niche circumstances, but it is definitely not very space efficient. Thanks for the question. Okay, so we're going to stick these things into the beginning of the array. Okay? And as we go along, we're going to leave, when we're done, when this second pointer here, this traveling pointer here gets to the end, then we're done. And everything from here to here, we don't care about. It's basically dead space, right? So we have two indices that travel for potential later use. Yeah, you can keep it around for potential later use. You have two indices to travel, and it gets from you know, every time you see a unique number, you copy it, and then you move it. Okay, so that's the algorithm we're gonna have. Okay, I'm gonna try out something. I'm gonna try out something since I have such an active audience here. Let me just type it in chat. Dear audience member, and you feel free to say no. Would you like to try doing the problem collaboratively? On a shared workspace. Oh, I don't like Python though. That's fine then. That's fine. I don't mean to pressure you. I don't mean to pressure you. It's always alright to say no. Just in general in life as well as when learning. Okay. It's just something that I'm sort of piloting because I have a Replit set up for collaborative programming. So in the future, maybe some other viewer wants to jump in and try that. Okay. All right. So, well, I see that you say you don't know Python, but I hope this stream is still useful to you. I think Python is a fairly intuitive language in many ways. So hopefully this stream is still useful to you. You can still follow along. Okay, so what we're going to do is we're going to do what we just described. So with nums, okay, we have 2 pointers. We have, let me draw that again. I regret not saving that picture. So we have 2 pointers. We have this pointer, and then we have a traveling pointer. Let's call it left and right. Let's call it current and travel. Current and travel. So the idea is that traveling pointer will move down the array. Current equals to 0. Traveling equals to 1. We're going to assume that the array is, the list is of at least size 2. So it's at least length 1. If it's exactly length 1, if length of nums equals to 1, then just return return 1. Then we're done. Okay, so assuming that is of at least size 2, what we're going to do is we're going to say while traveling smaller. Actually, I can use a for loop here. For traveling in range. So in Python, range creates an iterable, which is it will create this number that keeps going up every time you ask for it, and that can be used within a context of a for loop. So in range to length of nums minus 1. So it's going to start from it's going to start from so it's going to start from 1. Oh wow, not this. It's going to start from 1 and it's going to go all the way to here. And what we're going to do each time we travel is we're going to check if nums traveling is a new unique number, then copy it to current. Okay, so how do we know that nums traveling is a new unique number? How do we know that nums traveling is a new unique number? Well, we want to take advantage of the fact that this is a non-decreasing array. So this will be true when nums traveling is larger than nums current. So nums travel is first, it will start at 1, right? When it's at 1, it's not larger, this 0 here. This 0 here is not larger than this 0 over here. So it doesn't do anything. So we move it to here. So now t, this 1 is larger than this 0. So that tells us that traveling nums is now a new unique number. So what we have to do is to, 1, we'll copy it to current. We'll say current equals, current plus equals 1. So it increases by 1. And now nums current equals nums traveling. So we move current by 1 and then we copy it. We copy the new value. We copy the value for traveling to current. And I think this should work because this way traveling will keep moving. It will move all the way to the end. And as we go along, traveling will go to the next one. And then traveling will check, is num traveling larger than nums current? Nope, it's not. So keep moving. Is nums traveling larger than nums current? Well, it's still not. It's 1 and 1. Right? It's 1 and 1. So it's not. So keep moving. Is nums traveling larger than nums current? Well, looks like it is. So now we move nums current. It's kind of weird that I have to move the arrows one by one. And we copy nums traveling to here. So notice something very interesting. Nums traveling is 2, so we copy 2 to here. So notice something very interesting. Notice that everything after the current pointer, makes no sense. These things, I don't care. These things on the left, they are in ascending order. They are in ascending order. They are the result of what I want. So these things on the right, I basically don't care about them. It's going to keep going until it reaches the next one, which I think is going to be 3. And then travel will be, traveling will be all the way at the end. Oh, wow. This does not do what I think it does. Okay, traveling all the way at the end. And then C will be 3. And this will stop. Right? And you'll notice that at this point, everything to the right of this C, this current pointer, we can effectively discard. Which means the last thing we need to do is to return C. Sorry, C plus 1. C plus 1 because C is the index. And we want to return how many unique numbers there are. So we add 1 to the index. So this C or C plus 1, this is a classic example of off by 1. I was just about to say return C. If you're not sure if it's if it's plus 1 or minus 1 or nothing, then the sort of trick is to try it out. So I was just about to return C, then I looked at what C is. Well, C is 0, 1, 2, 3, but I want the answer to be 4, so it's probably going to be C plus 1. Would it be faster if you remove all the duplicates and then rearrange the numbers in non-decreasing order? If we remove all duplicates and arrange numbers in non-decreasing order, no, it will not. It will not. Because removing duplicates, think about how long it takes us for this algorithm to run. Well, there's only one for loop, right? And the for loop traverses the list exactly once. That's how long the algorithm takes. If we want to remove all duplicates, that actually takes a while. Imagine if your array, your list is not sorted in any way. If you want to find if something is a duplicate, that actually takes a while, right? That is, I believe, at least n log n. So this is O(n), and that takes at least n log n time to check if there are any duplicates. So let's run it. Pretty sure this should work. C is not defined. Oh, oops. Current. Wrong answer. Oh no. Output 1, expected 1, 2. Okay, let's make sure I'm doing the right thing. Nums equals we'll run twice, do those two things. It's not exactly that we have to do two things. It's that removing duplicates is hard. Removing duplicates takes a while. It takes longer than just the step of removing duplicates takes strictly longer than what it takes to run this algorithm. Arranging the numbers in non-decreasing order is also n log n operation. So if you want to do sorting is n log n at its fastest. Okay, let's see what's going on here. So we have a bug. Test case 1. Output 1. Interesting. Why is that? Length of nums equals to 2. I want to check if I'm modifying nums in a way I'm not supposed to. I don't see that. Why is my nums... Okay, so looking at this output, So the way debugging works, the way I like to do debugging is to find out what the output is getting wrong. It looks like it's getting the sort of length wrong. The length is wrong. Let's look at other cases and what the other cases do. So my output is 0, 1, 2, 3. Expected is 0, 1, 2, 3, 4. Wait a second. It means my current is 1 less than it should be. Let's try current plus 2. But I don't think this is correct. This is also wrong. Oh, I see. I see what's going on. Interesting. Can you explain why you have to add current plus 2? The reason why I tried current plus 2 is because I noticed that my output was, when I did current plus 1, my output was 1 smaller. You see how do I expand this? Well, I hope you can see it. I expected 1, 2, I only have 1. And the other test case, it expects 1, 2, 3, 0, 1, 2, 3, 4. I had 0, 1, 2, 3. So it looks like current is wrong because the length of the array, the length of the list that I'm returning is wrong. That's why I said current plus 2. I don't think it should be current plus 2. If current plus 2 work, I will have to think what exactly is going on that's going wrong. But let's see what's going on here. Oh, I think I know what the reason is. I think it's length nums minus 1. I think it should be length nums. Let's run it again. Oh, now it's correct. I see what the problem is. So length nums. Okay. So the problem was not the current. The problem was this line here. Length nums. So I want traveling to go all the way up to length nums minus 1, which is this guy over here, length nums minus 1. So in order to do that, I have to say length nums at the end of range instead of length nums minus 1. It's just like the way for loops work. It's just the way for loops work. Just like, in Java, you say for I smaller than 10, I plus plus, you not say I smaller than 10 minus 1. So a range basically iterates from the first number to 1 minus the last number. It doesn't go from 1 to length of nums. It goes from 1 to length of nums minus 1. Okay, cool. So let's try to submit this and see what happens. It beats 12% of users' memory. This is kind of sus, but it is what it is. It's sort of average speed. I wonder if I can get it faster by running it twice. Oh well, it's sort of average. I think most people got similar solutions. So I think that's it. That's how you solve today's problem. That's about it. I hope this was useful. I feel like the most important thing that I would take away from today is just this idea of packing the front of the array. This is actually a very common strategy. This idea of taking a large array and packing stuff into the front, ignoring what's behind. This is very common, especially for people working with C, C++. Okay, so I'm going to monitor the chat for any questions. If not, then my plan was actually to go back and sort of hunt my white whale. As people who have been watching this channel have known, my white whale is this sort list, which I've been trying to work on for the past 3 weeks, and it still doesn't work. I don't know why. I'm getting a little bit miffed, but that's okay, you know. Let me check if there's any questions in the chat about about today's problem. If not, then we're going to just call it for today's problem. I will continue hunting my white whale. So stay on if you want to continue hunting this white whale with me. Okay, let's come back to this. Sorting a linked list. Oh my god. So the last time we got an algorithm that works. Can you explain the speed? Yeah, sure. Let me come back to this real quick. So basically what this runtime does and memory does. Are you talking about this runtime and memory? Basically, this compares you with other users that have submitted correct solutions. And this means that I beat 58.40% of users who are also using Python 3. I beat this amount of people using memory. Of course, if you look at the code, my code actually did not allocate any additional memory. All I have are 2 variables. So I'm pretty sure other people use 2 variables also. So I don't think it's going to make much of a difference. Most of this memory actually comes from lists. So the runtime is very small. Because it's a small runtime, there's a lot of random fluctuations. Oh, whether my suggestion, how do you know? Let me see. How do you know the speed? Okay, cool. Okay, this is great. I love this question because I get to geek on and explain a few things. Okay, let me get rid of this guy. Okay, hold on. Let me just erase all of these guys. Okay, so how do I know? How do I measure the speed before even running? Well, I know because of computer science theory. Unfortunately, that's how I'm gonna say. But first, let me make sure that I understand you correctly, because I don't want to misrepresent your suggestion. It sounds like what you want to do is first. Let me see. Remove all the duplicates, then arrange numbers in non-decreasing order. So, would it be faster if you remove all the duplicates and then arrange numbers in non-decreasing order? So, are you talking about this particular problem? This particular problem where the input is guaranteed to be non-decreasing, or are you talking about the general case where the input can be anything? If the input can be anything, if the input can be anything, the input can be any order. You know, like 1, 3, 2, 10, 5, 7, 7, whatever. If the input can be anything, then trying to figure out what the duplicates are is actually n log n. You cannot do this in a single pass. So notice this code that we have here. This traveling goes from left to right. It just goes one time, left to right, and then you're done. So this is O n. Whereas if you want to remove duplicates, it is at minimum n log n, I believe. So the second step, I don't know what n log n is. Okay. You know what? I should do a mini lecture some other time. I'm collecting topics for mini lectures. So mini lectures is like 10 minutes to explain what time complexity is and big O notation is. So in a nutshell, this big O notation, O(n), means that let's say n is the length of the array. In general, n refers to the thing that most accurately represents the scaling factor of the problem. So the larger that we want to know how fast algorithm width is when we increase the array to very large numbers. So we use n to represent the size of the array. So because your for loop only runs one time from left to right, it's an O(n) operation. It takes linear time. It's O(n). So you think about a problem like finding duplicates in an unordered array. That takes at least n log n time. Or better yet, you think about sorting. You want to have a bunch of things, right? You want to sort them in the right order. That takes at least n log n time also. You cannot do that in log n time, generally speaking, without consuming a lot of a tremendous amount of space. So you cannot do this in log n. You cannot do this in O(n) time. Because you think about it, right? Let's say you have these 1, 2, 3, 4, 5, 6, 7 things. How do you arrange them from smallest to largest? Well, the first thing you need to do is to figure out who is the smallest. So that already is an O(n) operation. And then you want to put, let's say you want to put this 2. You want to put this 2 here, and then the 3 on the other side. And then you have to figure out what's the next smallest one. You have to arrange things around. So this process definitely takes longer. This shuffling things around definitely takes longer than just one single for loop traveling from left to right. Does that make sense? So the reason why I know is that n log n is because this is just CS theory. I don't think I can explain it adequately right now, but I will try it in a different video. So n log n log of n I think doesn't need explaining, right? So n log n is slightly above linear time. I hope that was helpful. Okay. Is that okay? Okay, I will make an explainer video about this though. I will have to think a little bit about it. I will think about what's the best way to explain this. I think I have to think a little bit about how to explain it. But the general idea is you don't always have to write code to figure out or you don't have to time things to figure out how fast things go. You can estimate them based on the structure of your code. Take for example, okay, let me see if I can explain this concept very, very quickly right now. So take for example, let's say if I have one for loop, right? Okay, Let me choose a new one. Okay, let's take for example, right? I'm going to give you 3 different algorithms. And you can tell me which one you think is the fastest. Okay, I'm going to give you 3 algorithms. Let's see if we can explain this really quickly. So let's look at these 3 algorithms. Algorithm 1 is just a simple for loop. It goes from left to right. The number of times it executes an instruction would be proportionate to the length of the array. So that's very simple. Right? But what about algorithm 2 and 3? So obviously algorithm 1 will be the fastest. Of algorithm 2 and 3, which one do you think is faster when nums is very long? When the length of the array is very, very large, do you think algorithm 2 will be faster or algorithm 3 will be faster? Well, if you said algorithm 3, you'll be right. Algorithm 3 will be faster than algorithm 2. Because if you look at algorithm 3, it's doing this n times. Or let's say n is the length of nums. It's going to do this another n times. Yes, because algorithm 2 is wrapped within the other one. Yeah, so this is actually n squared times. So when n is very large, this is actually 2n. So 2n will be much larger than n squared, and this is n. So obviously this is the fastest. I think that's the easiest way to think about it. I hope that makes sense. I will try to get a better explainer video once I think about it a little bit. I want to make a very short video because I feel like if I give a 1.5 hour lecture, nobody's going to listen. So maybe a 5 to 10 minute lecture lesson that just covers the most important points. But I have to think about it a little bit. Okay, cool. We have another 13 minutes, so I'm going to hunt my... I'm sorry, I'm very invested in doing this. I'm actually super invested in doing this. Let me check, make sure there are no other questions from the chat. If there are questions, keep asking, by the way. I'm just really invested in trying to get this problem done. Okay. Okay, I see no other question. So for those of you who are still around and remember this problem from the last time, this very annoying and also very interesting problem. I'm pretty sure there are easier ways to do it, but I refuse to do it the easier way because this way is way more fun. We were trying to write quicksort, make quicksort work on linked lists. And the problem we ran into, so we did it the last time, we were successful, but the problem we ran into is that quicksort is very often written recursively, which is not good when the input is very large, because we run into the problem of maximum recursion depth. Which, if people are interested in, could be another lecture. So we are trying to refactor this algorithm to make this iterative and not recursive, so we don't run into maximum recursion depth. So I have about 11 minutes to do this, since I'm streaming for 11 more minutes. So we're gonna see how far we can get with this. Okay, so we have a new algorithm for removing the recursive call, and basically we're gonna use a stack. And the way it works is, we're gonna push. Okay, if we're gonna do this helper thing, we're gonna get the before, the mid, and the after. But instead of stitching them, instead of calling this step, we're gonna take these three things and we're gonna put them into a stack. We're gonna put this into a stack. Okay? We're gonna push it down into a stack. And by the way, I'm drawing this for the benefit of you guys, but also for my own benefit. So for instance, this 4213 would be after first, and then 213. Okay, and we're gonna sort 213. We're gonna sort 213. We'll pop one item out. We're gonna sort it, and then 213 will become so 3, 2, and 1. And then because this is one item, we'll just pop it. Okay, cool. I think we got it. I think this is go. I think we have it. All right. All right, team. For those of you who are still around on the stream, hunting this elusive whale with me, thank you for staying on. We're gonna see what we're gonna do. All right, so we're gonna refactor out. So here's my plan. I'm gonna create a stack. Gonna use a list to simulate a stack. We are going to helper head. Okay, so self.helper head, we're gonna give it also the stack. And what else are we gonna do? We're gonna put a few things on the stack actually. So each time we put something on the stack, we're gonna put let me see. Let's not return anything first. Let's be super fast about it. Okay, we're gonna not do this also. So we have this, right? We have mid with the fulcrum. We have before, we have last. I don't think we need last. I don't think we need after. We just need mid, before, and after. So what we're gonna do is, we don't need last, before, we don't need after. Let's keep this. Okay, after we do this, we're gonna push these guys down onto the stack. Actually, we're not even gonna do that. Let's do this thing. Alright, thanks, Chien. Bye. Return. before, mid, after. Okay, so we have helper, which takes head, breaks it up into before, mid, and after, and returns these three things. Mid is the essentially head, the old head. Before is everybody smaller than mid, and after is everybody larger than mid. Okay, so we're gonna take this, we're gonna put it on the stack. We're gonna put it before, we're gonna put it after. Can I have a... Is there a ready-made stack in Python? No. Okay, so you can just use a list. We're gonna use a list, okay? We're gonna say dot append after stack dot append mid, stack dot append before. Then we're gonna do a thing. We're gonna say we're gonna take the last thing from the stack. While length of stack greater than 0. Results. Okay, we're gonna mess around with this a little bit. Results. Okay, so we're gonna mess around a little bit. So the idea here is we keep a stack. This stack is essentially our work queue. You know, the things that we still have to work on. Alright? So in each iteration, we pop the last element, the topmost element on the stack. We run it through our helper, which will split it into before, after, and mid. And we push those things back onto the stack in the order we did it in. So item. Okay, let me see. If after not none, push after. Likewise, if before not equals none, push before. So we don't want them to push none. If they're none, don't push it. Because before and after could both be none if they're empty. Mid is guaranteed not to be none. Mid will never be none. Okay, so we check if length of item equals to 1, then we add it to result. Else, we do our thing. Okay? So what this does is it will take head, it will split it into 3, before, mid, and after, stick it into the stack, and then pop the first thing on the stack, work on that. If it's you split it up, if you need to, put it back on the stack. And then you keep doing until you pop the topmost item is 1, then you just append it to result. So if results equals none, results equals item, We need last result. Last result. Dot next equals item. Okay, cool. Last result dot next equals none. I think this should work. Also, these are famous last words. When somebody says, I think this should work, it's almost a guarantee that it will not work. Huh. But you know what? My dear white whale, I will hunt you today. Let's run it and see what happens. Syntax error. Okay, that was very anticlimactic. Let's run it again. List node has no length. 74. Oh, sorry, not length, but item dot next equals to none. This will be very, very slow, I think. Not enough values to unpack. 3 got 2. Is there a different return item? Head. Wait, before and after? Oh, no. None. Hit none. Yep. This is going to be very slow because it's clunky. But that's okay. Oh, time limit exceeded. Interesting. So it doesn't even finish for the most basic values. Oh, okay. So I see. Stack equals to stack. So we're going to pop the last element and then we're going to delete it. None type value has no attribute next. 75. If item, how does none get onto the stack? Oh god. Interesting. Well, I think we made progress. We have some kind of strategy going forward. I believe this should do the right thing. I believe this piece of code should work. I don't know why it's not working, but we're gonna try and figure that out next time. Alright. So next time we're gonna work on is subsequence. This is going to be next week's problem. Those of you at home can try to work on it on yourself before coming to the stream. I'm going to put it up. Oh, actually, next time, this Saturday, I'm going to do the programming contest. Come by if you're interested to support me, watch, and maybe even join the contest yourself. Maybe you'll do even better than I will. I will be very happy if you do. But next week, when we come back to the lesson proper, we're going to do is subsequence. That's number 392 on the website. Okay, with that, it's time for me to sign off. Thank you everybody for watching. Goodbye.